too.
Let's see. All right, now we're live.
Hmm. Um,
I've
I'll
been
pull it up.
I've been wondering if we should go back to reading the book. Maybe until if someone pops in, I guess we could read less, perhaps explain more.
Yeah, yeah. I mean, we could. Yeah, for certain parts, we could potentially read the book.
Yeah. So I remember last time we went through this, reading the book was pretty enlightening. Um, hmm.
Yeah, yeah. I mean, we could like for some parts we could kind of read the book and then discuss.
Yeah. Let's see. Unless you think it'd be better to just like read it in our heads. I'm not entirely sure.
Yeah. Mm, Well, see, I guess. Um, yeah. I mean, there's some parts where it might be better to read the explanation, but like, I mean, I guess like this part we could like kind of like summarize it. Because like I guess the initial idea is that like so you got a circuits can be modeled using logic. Um, and I guess like at the like a high level kind of abstract level, I think the general idea is that like whenever you have something like kind of some signals or some input or just any variable or something that can have two possible values, you can model that using logic. And you can just say like you can call the two values true and false. And then when you have like different systems where you have like many things, each of them can have two values and they're kind of like coming together to produce some output. You can model that using logic because like in logic, you got like you can have complex statements that are made up of many smaller statements, and the smaller statements each have one of two values, true or false. And then like the truth values of the component statements combine to give you the truth value of the whole statement. So similarly, like you can have in real life like different systems where you have like many different things. Each of them has two values, and they kind of combine to give like some output value. Whenever you have that, you can potentially model it using logic. So that's what we have here, like with circuits. Like uh, like a circuit, I guess it's kind of like a wire. Like an electric current flows through it, and like the circuit in a sense it has like it can have two possible states, like two possible values associated with it. It can be open, so like at the bottom there's the diagram that shows like when the circuit is open, like there's kind of like the two parts are not connected, so the current an electric current can't flow through. um and then when the circuit is closed, the two parts are connected, so a current can flow through it. So a circuit has like these two possible states. It can be open or it can be closed. And then on the right, there's a diagram where you have like a light bulb connected to the circuit. And that like oval thing is a light bulb. And so if the circuit is closed, then the current can flow through the circuit so it can go into the light bulb and the light bulb will turn on. But if the circuit is open, then the current can't flow, so the light bulb will stay off. Um, yeah, so that's kind of the general idea of circuits. And circuits, yeah, we have like the two possible values associated with them. They can be open or closed. And we're going to end up kind of using logic and like referring to open and closed as true and false. So hopefully anyone like who like watches the stream or watches it later, hopefully it sparks your interest.
It actually does sound way funner than I thought it'd be.
Yeah. Yeah, so that's kind of the setup for it.
Interesting.
And then like in the next part, like you can combine multiple different circuits together.
Right. Let's see. I guess I will go ahead and read this paragraph. From the late 1930s, a young MIT graduate named Claude Shannon noticed an analogy between the operations of switching devices, such as telephone switching circuits, and the operations of logical connectives. He used this analogy with striking success to solve problems in circuit design and wrote up his results in his master's thesis, which was published in 1938. So let's see. The drawing in figure 2.4.1 shows the appearance of two positions of a simple switch. When the switch is closed, current can flow from one terminal to the other. When it's open, current cannot flow. Imagine that such a switch is part of the circuit shown. The light bulb turns on if and only if current flows through it. And this happens if and only if the switch is closed. Hmm.
Yeah. Yeah, I like how this section is talking about applications, kind of switching it up.
Yeah, I wonder if it's like I wonder if it's true that it only turns on if and only if the switch is closed. I guess, and not if the switch is closed.
Yeah. Well, I guess if you add like it's only if the switch is closed, that means like if the switch isn't closed, then it's not gonna turn on.
Right.
Um,
Yeah. I guess
but
that's obvious.
yeah, yeah, I guess because if the switch is open, then the current can't flow through.
Okay. So the more complicated one. A switch, the light bulb only turns on if and only if P and Q are closed.
Yeah,
So I wonder if the switch being closed would be considered true for that variable or false. I guess it'd be considered true to make things simpler. So like P and Q, if and only if the light bulb is on.
yeah, yeah, exactly. Yeah, on the left one, because you need both of them to be closed in order for the current to flow through.
Interesting. I guess if the light bulb was just L, then we could say, let's see if this P and Q if and only if L, right? And then I don't know what this thing is. Maybe that's just where the power is coming from. No,
Yeah, I
maybe,
guess so. I'm not
yeah.
sure what that is.
It's like the beginning and the end of the circuit, it looks like.
Yeah,
Because I don't know if they go over it here, but I'm pretty sure like the volts have to come in somewhere and there also has to be a ground for the circuit to, like, for the electricity to go.
yeah, yeah. So that might be what that is.
Interesting. Okay, and then on this side, it's more like P or Q if and only if L, right?
Yeah. Yeah, so here it's like the current has two possible paths it can take to get to the light bulb. And if one of them is closed, then it's able to get to the light bulb.
Okay. Interesting. I guess maybe I will like like I could send out an announcement because I think people might enjoy this one.
Yeah, 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 that's really interesting and kind of
Yeah.
unexpected. I wouldn't have thought that logic could be related to like electronics.
Me neither. I wouldn't have thought it'd be so simple.
Yeah,
Mm. All right, let's see.
yeah.
So,
So we got the is the terminology for those in series versus in parallel. And the
okay,
switches are like in series if they've got to both be closed for the light bulb to turn on. And then they're parallel if like at least one needs to be closed. And then that reflects like how they look visually, like P and Q. They're like in a series, they appear one after the other. But then in the left diagram, but in the right diagram, like even physically they're parallel to each other. So they're kind of providing two different possible paths that the current can take to get to the light bulb. And as
makes
long as at least one
sense.
of the paths is closed, then the current's able to get there.
Makes sense. What is this? Some kind of truth table?
Oh yeah, it's pretty much a truth table. Um yeah, they used closed, open, and on and off. And then I think on the next page they're gonna kind of turn those into true and false.
Okay.
Yeah, so like when they're when the switches are both when they're in series, that means they've got to both be closed for the light bulb to turn on.
Right.
Yeah, and then that shows it looks a lot like you said, it looks a lot like a truth table. So you can just replace closed with true, like you said, and then open with false.
Makes sense.
Yeah, and then on would also be true and off would be false.
Hmm. Right.
Yeah, because then we end up getting exactly the truth tables for P and Q on the left, and then P or Q on the right.
Interesting.
Yeah, and I guess you could kind of think of P and Q as being like P could be like the statement switch P is closed, and Q could be the statement switch Q is closed.
Right.
Yeah, and then you're looking at like the relationship between those and the statement that the light bulb is on.
I'm just impressed at how cleanly it fits with the logic that we've been learning.
Yeah, yeah, it's really cool.
Hmm. It
Yeah,
says
and then it
in 1940s and 50s, the switches were replaced with electronic devices. with the physical states of closed and open corresponding to electronic states such as high and low voltages. Okay. The new electronic technology led to the development of modern digital systems such as electronic computers, electronic telephone switching systems, traffic light controls, electronic calculators, and control mechanisms used in hundreds of types of electronic equipment. Digital logic. Okay, the basic electronic components of a digital system are called digital logic circuits. The word logic indicates the important role of logic in design of such circuits, such as digital. And the word digital indicates that the circuits process discrete or separate signals as opposed to continuous ones. That looks like a lot of circuitry.
Yeah.
CPU. Ah,
Oh, that's interesting. I can read this paragraph here.
okay.
So, oh, it's I mean the one above the black boxes and gates.
Was it?
Yes, so like
Yeah.
electrical engineers continue to use the language of logic when they refer to values of signals produced by an electronic switch as being true or false, but they generally use the symbols 1 and 0 rather than T and F to denote these values. The symbols 0 and 1 are called bits, short for binary digits. This terminology was introduced in 1946 by the statistician John Tukey. Well, I never knew that bits was short for binary digits. That's interesting.
Me neither. Black boxes and gates. Combinations of such signal bits, ones and zeros, can be transformed into other combinations of signal bits, one and zero, by means of various circuits. Because a variety of different technologies are used in circuit construction, computer engineers and digital system designers find it useful to think of certain basic circuits as black boxes. The inside of a black box contains the detailed implementation of the circuit and is often ignored while attention is focused on the relation between the input and output signals. Hmm. The operation of a black box is completely specified by constructing an input output table that lists all its possible input signals together with their corresponding output signals. I can kind of see where this is going.
Yeah.
Like, in terms of logic, there may be some kind of what do you call it?
It's well, it's kind of like in logic how like the inputs are going to correspond to like the individual statement variables, and then like the output will be like the truth value of the compound statement.
Exactly, the truth value of the compound statement. And it's kind of unpredictable because the compound statement can be just like infinitely complex.
Yeah. Yeah, and so you can use kind of like different statements like to model whatever input output system you want to model.
Right. You can use a truth table. So even though there's infinite complexity, um, you can still see all of the possible outputs based on all the possible inputs,
Yeah.
combinations. Okay, so the operation of a black box is completely specified by constructing an input-output table that lists all the possible input signals together with the corresponding output signals. For example, black box pictured above has 3 input signals, and each of these signals can take the value 1 or 0. There are 8 possible combinations of input signals. One possible correspondence of input to output signals is as follows. Right, so there's the 8 possibilities that we get from having 3 input signals. So we only have 8 output signals to list. That allows us to use that black box without knowing its inner complexity.
Yeah.
The third row, for instance, indicates that for inputs p equals 1, q equals 0, and r equals 1, the output is s equals 0. An efficient method for designing more complicated circuits is to build them by connecting less complicated black box circuits. 3 such circuits are known as NOT, and OR gates. Okay, let's see. Hmm.
And I can do this part here.
Okay.
Yeah, a NOT gate or inverter is a circuit with one input signal and one output signal. If the input signal is 1, the output signal is 0. Conversely, if the input signal is 0, then the output signal is 1. So it's called a NOT gate because it does the same thing as as NOT in logic. Because like if you have a statement variable and you put NOT in front of it, um, then like if the statement variable has a truth value of true or 1, then like not like if p has a truth value of 1, then not p has a truth value of 0, and if p has a truth value of 0, not p has a truth value of 1. So it's called a NOT gate because like the way it works is just like how NOT works in logic. Like
Makes
it takes one truth value and converts it to the reverse.
makes sense.
Yeah. Um, and then an AND gate is a circuit with 2 input signals and 1 output signal. If both input signals are 1, then the output signal is 1. Otherwise, the output signal is 0. So that's also just like AND in logic. Like if you have P and Q, then that has a truth value of true or 1. If both of the statement variables have a truth value of 1, and then it has a truth value of 0 otherwise, because like a conjunction is true just in the case where both of the individual parts are true. So this also works just like AND in logic. And then an OR gate also has 2 input signals and 1 output signal. If both input signals are 0, then the output signal is 0. Otherwise, the output signal is 1. So that's also just like OR in logic, because like if you have P or Q, that's going to be true if at least one of P or Q is true. It's only going to be false if both P and Q are false. So here we have like you're putting in 2 signals, and you're going to get an output of 1, except when both of the inputs are 0, then you get an output of 0. So it's just like OR in logic. P or Q is only false if both P and Q have a truth value of false, which is represented by 0 here. Yeah, so the actions of NOT and OR gates are summarized in figure 2.4.3, where P and Q represent input signals and R represents the output signal. It should be clear from figure 2.4.3 that the actions of the NOT and OR gates on signals correspond exactly to those of the logical connectives NOT and OR on statements. If the symbol 1 is identified with T, true, and the symbol 0 is identified with F. And then gates can be combined into circuits in a variety of ways. If the rules shown in the next page is obeyed, the result is a combinational circuit, one whose output at any time is completely determined by its input at that time, without regard to previous inputs. So this is going to end up being kind of like how in logic, like you can make complex compound statements, and then you can kind of use the rules for the truth values of the connectives to figure out the truth value of the whole thing.
Makes sense.
Yeah, so those
Okay.
are like the tables like showing for the inputs, what output do you get for each of the gates? And then the gates are kind of represented with different shapes. And like those are those are black boxes. Like some stuff happens in between, but we're not worried about what happens in between. We're just looking at for a given input, what is the output?
Oh, I see. Okay. Well, I know how not and or works, so this is pretty intuitive.
Yeah,
So the rules for combinational circuits. Never combine two input wires. Okay, like a single
yeah. I
input
wonder.
wire can be split part way and used as input for two separate gates. Oh, that's cool. So you can do like this. Uh, for example.
Yeah,
An output wire can be used as input. Makes sense. Like these two could go into a, let's see, OR gate. No output of a gate can eventually feed back into that same gate. Oh, I didn't know that, so I couldn't. Well, I mean, there's not really any more spots for it to feed back into anyway.
yeah, yeah. I guess it's like it can't go in a circle.
Um, like, like
Kind of like with
this.
like you have the gate, and then there's like a circuit coming from that gate, and then it circles around and goes back into the gate.
Huh.
Yeah.
Um, no output of a gate. What if it goes through another gate first? Like,
I think that's not allowed either. So you could have like another gate of the same type later on, but it can't go into like the same exact gate again a second time.
interesting. Yeah, I guess that might produce some issues, maybe.
Yeah. Yeah. Although I guess here they say that there are some circuits that do that.
Do they say that?
Oh, above the input output table.
Oh, okay. Called sequential circuits. Interesting. Whose output at any given time depends on the input at that time and also on previous inputs. These circuits are discussed in section 12.2.
Oh, that's something to look forward to. I wonder how those would work.
Interesting. I guess, yeah, I guess there are some like situations in logic where it's more like a sequential logic and yeah, whatever the result is depending on what the result of the previous logical conclusion was.
Yeah. Yeah, exactly, and but, like, look, with the circuits that we have in this section, it's kinda just like, at any given gate, you just need to look at what the input is, and then you know what the output is.
Right. So, if you're given a set of input signals for a circuit, you can find its output by tracing through the circuit gate by gate. Okay, an example. Um, let's see here. Indicate the output of the circuit shown below for the given input signals.
Yeah, so for this, it could be maybe we can, like, write the value of this signals, like, at different points along the way. So, like, at the starting point, like, P has a value of 0, and then Q has a value of 1.
Okay, so P is 0, then at this point it's 1, and at Q is 1, so R is going to be 1. And then over here, P is 1 and Q is 0, so the output of the OR gate would be 1. And you go to the NOT gate, it would be 0. They said R is 1 here. 1 and 0 would result in 0.
Yeah,
Okay.
yeah,
To construct the entire input-output table for a circuit, trace the circuit to find the corresponding output signals for each possible combination. Wonder. Okay, I don't think they asked us to do that yet. Oh, now they are. Construct the input-output table for a circuit. So, do you want to
oh,
do
yeah.
this one?
Yeah, that sounds good. So I guess to make the input-output table, so our inputs are P and Q, so we'll have columns for P and Q, and then the outputs are, so then there'll be a column for R.
So we have.
Yeah. So then, I guess we can start by filling in, like, the possible combinations of values for P and Q. So we could have, like, 1, 1. Yeah, exactly. Yeah, 1, 1, 1, 0, 0, 1, or 0, 0. And then looking at each possibility, so starting out with 1, 1. So we have P is 1, and then Q is 1, so the 1 goes through the NOT gate, that becomes 0. So we have inputs of 1 and 0 going into the OR gate, so that's gonna give us 1 for R in the first row. Yeah, and then the next row, so we have, P has a value of 1, and then Q is 0, so the 0 goes through the NOT gate, and it becomes 1. Um, so we have a 1 and a 1 going into the OR gate, so that's also gonna give us 1 as the output. And then for the next row, 0, 1, so we got a 0 for P, and then Q has a value of 1. The 1 goes through the NOT gate and becomes 0. So we have a 0 and a 0 going into the OR gate, so yeah, we get 0 for the output. And then the last row, P and Q both have values of 0. So for Q, the 0 goes through the NOT gate and becomes 1. So we've got a 0 and a 1 going through the OR gate, and so we'll get an output of 1.
Hmm.
Yeah. Yeah, yeah, really cool how it's, how logic can be useful for describing circuits.
Yeah. I almost feel like circuits can be useful for describing logic, but I guess.
Yeah, yeah, it could go both ways, definitely.
Hmm.
Yeah, yeah, I can read this part. The Boolean expression corresponding to a circuit. In logic, variables such as p, q, and r represent statements, and a statement can have one of only two truth values, t true or f false. A statement form is an expression such as p and not q or r, composed of statement variables and logical connectives. The logical connectives are like and, not, and or. Um, as noted earlier, one of the founders of symbolic logic was the English mathematician George Boole. In his honor, any variable, such as a statement variable or an input signal, that can take one of only two values is called a Boolean variable. An expression composed of Boolean variables and the connectives not, and or is called a Boolean expression. Given a circuit consisting of not, and or gates, a corresponding Boolean expression can be obtained by tracing the actions of the gates on the input variables. Yeah, so the key point is that like any variable that can take exactly two values is called a Boolean variable. Like in logic, a statement can be true or false, so we can kind of use logic to model any sort of variable that can take two values. And then a Boolean expression is where you've got Boolean variables combined with with these three logical connectives. And then we can represent different circuits using Boolean expressions. Because then we'll represent them with expressions where the truth table of the expression corresponds to the input output action of the gates.
Okay, okay. So the first one, I suppose, would be we have P or Q, but we also have P and Q. I guess in terms of Boolean expression, parallel gates would be represented with an AND operator.
Uh, let's see. Um, so we got yeah, yes, yeah, yeah. So we got the P or Q is one of the inputs into the AND gate, or the out like the output of P or Q goes into the AND gate, and then the other thing that goes into the AND gate is yeah P not oh yeah it'll be not P and Q
Ah,
on the right.
right.
Is we take a P and Q and then we apply a NOT gate to it. So we'll have P or Q and not P and Q. Yeah, exactly.
Interesting. And then over here we'd have P and Q and not R.
Yeah.
Okay. One second. Okay.
Yeah.
So let's see.
As they point out that like for this one where we've got the Boolean expression P and Q and not R, there's only one combination of inputs that'll give an output of 1. P equals 1, Q equals 1, and R equals 0. Because there you'd have like P and Q, both P and Q have truth values of 1. So P and Q has a truth value of 1. And then if R has a truth value of 0, not R has a truth value of 1. And then you have a conjunction of two things, both with truth values of 1, P and Q, and not R. So you'd have a truth value of 1 for the whole thing. But that's the only case where you get a truth value of 1.
Interesting.
Because for a conjunction, you only get a truth value of 1 when both of the conjuncts have truth values of 1. So it has a truth value of 1 for just one combination of inputs and 0 for all other combinations of inputs.
Oh, yeah, that makes sense.
Yeah. It says, for this reason, the circuit can be said to recognize one particular combination of inputs. The output column of the input-output table has a 1 in exactly one row and 0 in all other rows. Oh,
Hmm.
that's interesting.
A recognizer is a circuit that outputs a 1 for exactly one particular combination of input signals and output zeros for all other combinations. Okay. Interesting.
Well, yeah, I could imagine that would be useful in electronics. Like maybe you want something that's sensitive to a particular input. Like, yeah, I wonder
Right.
what situation you would need that. But maybe like I don't know if this is how it works, but like a computer only turns on with a certain password, and maybe that involves a recognizer.
Ooh.
Yeah, I don't know if it does, but maybe on some level it ends up involving like some sort of very complicated recognizer.
Yeah. Like maybe you can press any other button on the computer and it won't turn on, but it'll only turn on if the power button is pressed.
Yeah, yeah, that's really interesting.
Okay. The preceding examples showed how to find a Boolean expression corresponding to a circuit. The following example shows how to construct a circuit corresponding to a Boolean expression. Okay. Construct circuits for the following Boolean expressions: not P and Q or not Q. So I don't know. I wonder what like the strategy is for constructing these. I'd actually start from the or not Q because that seems pretty simple.
Yeah,
So at the end, there's going to be a or, and at the beginning, there's going to be a Q going through the not gate. So on the other
yeah,
side, we have not P and Q. So at some point, there's an AND gate, and then there's P going through a NOT gate, and Q, I guess I can solder from here
yeah,
into the AND gate.
yeah, yeah. I think that's what it would be.
Okay. And the other one
Yeah,
is,
yeah, and then
you want to try this one? P and Q and R and S and t.
Yeah, yeah, I'll try it. Yeah, I like your strategy of kind of working backwards. Because yeah, I guess here we'd have like so we have two things going through the AND gate at the end. We have this big thing P and Q and RNS, and then we have T. So I guess at the end there's an AND gate, and there's T going through it. Yeah, and T just goes directly into it. Yeah, and then before that AND gate, we've got another AND gate, and that's going to have P and Q going into it, and also RNS going into it. Yeah, and then the AND gate, that AND gate has two inputs, and each of the or two input wires, and each of those input wires has another AND gate. Yeah, and then into one of them we have P and Q going in, and then the other one RNS. Yeah, yeah, that's really cool. I guess that's kind of really like is useful for like really kind of understanding the structure of these statements.
Right. Yeah, it's interesting. It's like a visualizer. Somehow it's more visual than this like more flat text representation.
Yeah.
Let's see. Just write the input variables in a column on the left side of the diagram. I wonder what that means.
I think that kind of just means you have them like I think they're working the opposite direction, so they just like write all of the variables on the left. So we do have that
Oh,
like in yeah, we have PQ on the far left of the diagram, and then PQRS and T, all of them there on the left.
that says then go to from the right side of the diagram to the left, working from the
Oh yeah. Oh
outermost
yes, that's
part.
the strategy that you came up with.
Hmm. It seems a little awkward to write the variables to the left and then start from the right, because how do you know exactly where the variables will end up?
Yeah. Yeah, I agree. I think yeah, I do think it's easier to kind of just go right away to the far right of it, and then work from there.
Interesting. I mean, I'll try it their way next time, though. See. Like, if we started off with a limited diagram space to work with, then maybe I could see how their way fits into this. Okay.
That looks like what we have.
Yeah.
Yes, definitely the Boolean expressions are very powerful. They're unstoppable. Yeah,
Unstoppable.
yeah.
That sounded like it was meant to be a pun, but I don't think it was.
Yeah, it's like a semi-pun unstoppable.
Unstoppable?
Yeah, it's like Boolean expressions are unstoppable. So it's like a sort of
Oh,
one-ish thing.
unstoppable.
Yeah.
Let's
Oh,
see.
interesting.
Um, it follows from theorem 2.1.1 that all the ways of adding parentheses are logically equivalent. Thus, for example, okay. It also follows that the circuit in figure 2.4.5, which corresponds to uh, P and R and S and T, has the same input output table as the circuit in 2.4.4, which corresponds to P and Q and R and S and T. Maybe the point here is that those theorems in logic apply to logic gates.
Yeah. Yeah, and I guess the theorem they're talking about is probably like associativity, like the idea that when you have like a bunch of ands, the where you put the parentheses doesn't matter.
Yeah.
Yeah, that's cool. So those circuit no matter how you structure the circuits, like if it corresponds to like putting the parentheses one way versus another, you're gonna have the same result and it'll have the same action on the inputs.
Yeah. Okay. Each of the circuits is therefore an implementation of the expression P and Q and R and S and T. Such a circuit is called a multi-input AND gate and is represented by the diagram shown. Multi-input OR gates are constructed similarly. Whoa. Oh. So it can be simplified that way.
Oh yeah, I like that.
Yeah, me too.
Yeah, it looks kind of like a jellyfish.
It does. It does a very like digital jellyfish because of these sharp edges that's tentacles.
Yeah. Oh, cool.
Finding a circuit that corresponds to a given input output table. To this point,
I could read.
oh, go ahead.
To this point, we have discussed how to construct the input-output table for a circuit, how to find the Boolean expression corresponding to a given circuit, and how to construct the circuit corresponding to a given Boolean expression. Now we address the question of how to design a circuit or find a Boolean expression corresponding to a given input-output table. The way to do this is to put several recognizers together in parallel.
Okay. Designing a circuit for a given input output table. Design a circuit for the following input output table. And their tip is to put multiple recognizers together.
Yeah, where a recognizer outputs a truth value of 1 for only one possible combination of inputs.
Okay, well, let's
So,
see. There might be three recognizers required here.
oh yeah, yeah, oh yeah, exactly, 1 for each row.
So we need a recognizer. I mean, once we have the recognizers, what do we do with them? Oh, we put them in parallel.
Yeah, because then if they're parallel, it's like kind of saying like this one or this one or this one.
Oh, right. So in parallel really means like we or them together. I
Yeah,
yeah, I
yeah,
guess if you
or
just the strategy is just to or recognizers together until you get the input output table you're looking for.
yeah, I think so. Yeah, or maybe I guess you could represent it with an OR gate, although maybe like even if you just like physically put them parallel, maybe that'll already have the effect. Like if you kind of have all three of them and each one like branches off into like three different parallel um directions. But
Hmm.
yeah, but I guess I guess maybe like for each of the parallel parts, we need to come up with like a Boolean expression that will give a truth value of 1 just for that combination.
So let's see here. They're saying we have a P, a Q, and an R, and they're going into a circuit that we're about to create, right? That
Yeah,
produces an S um, in accordance with this input output table.
yeah,
Okay, and we could actually just create 3 recognizers. And then I was thinking, if those recognizers all went into an OR gate, it,
oh yeah,
it would produce the desired result.
oh yeah, exactly. That makes sense. Yeah, yeah, it would because you would have like at least one of the recognizers would have to come out true, and that's what we want. Yeah.
Mm-hmm.
Yeah, and then
Okay.
to make the recognizers, we need to find like what would be an expression or like a combination of gates that'll give us like for each of those combinations of inputs that'll give us an output of 1 just for that combination.
Well, the first one's an easy one because you can just use an and multi-input AND gate.
Yeah, yeah, exactly. And that'll correspond to the Boolean expression P and Q and R, which is only true when P, Q, and R are all true. Yeah, so that'll be one recognizer, and then the third row, 1, 0, 1. I
Mm-hmm.
guess for that, I guess for the Boolean expression, you could have like P and not Q and R, I guess.
Oh, that makes sense. So it's another AND gate, but you just threw a NOT gate in front of the Q.
Yeah.
I think a recognizer almost always ends with an AND gate. Maybe not, but like it's very easy to do it that way.
Yeah.
Because here we just have 2 NOT gates again, right?
Yeah. Yeah, exactly. Yeah, for the 1, 0, 0, we're gonna have like the expression Boolean expression would be like P and not Q and not R.
Mm-hmm. Did you expect the electronics to be so reasonable, so in alignment with what you already know?
Oh, yeah, yeah, I didn't expect that. Yeah, it's definitely very like very nice and elegant in its use of the logic.
Right? All right, so those are the things. And then we just could literally just put them into a OR gate to get the desired result.
Yeah. Yeah, and then also I guess we would have like the each of the wires would be soldered like maybe like the middle each of the middle ones could have like a branch like with a dot going off into the other two like like each like the P in the middle could have like a branch going to the other
Oh,
P and then the other P at the bottom.
all right, let's see. Like, you mean like instead of duplicating them?
Yeah, I think like yeah, so you'd have them soldered, I think, because like each P is kind of like the same signal, like the same one input that's going in.
True.
Yeah. Oh yeah, that's a good way of doing it. Yeah, they can have like the
Um, so
yeah. Yeah, and it'll be kind of tangled, but I guess you'd have the same thing for the Q and the R.
right. Yeah, I wonder what their like wire management strategy is.
Yeah, maybe they use like dotted lines for one of the wires and or like maybe like a squiggle or something for another. I don't know though.
Like,
Yeah,
what
I'm curious to see
rules
how they did it.
dictate where you put the soldering dot?
Oh yeah, I don't know where. Yeah, I'm not sure where it's best to put them. I think that looks good, but yeah, I'm curious to see how they draw it.
Yeah. Okay, let's see. Solution. First, construct a Boolean expression with this table as its truth table. A
Yeah,
Boolean
yeah, and that one
expression.
there is what we have.
I don't think we constructed a Boolean expression, did we?
Yeah, well we kind of like for each row, like the first row you had like P ends Q and R. The second row we had like P ends not Q and
Oh,
R.
okay.
Yeah, and then you combine all of them with an or. So that expression that they have there is pretty much what we were doing.
A Boolean. So, right, we did construct a Boolean expression for each of the recognizers.
Yeah. And then like combining all the recognizers with an OR gate, that's equivalent to like putting
Oh,
ORs between each of the Boolean expressions.
I see. Did this
Yeah, so
identify?
that thing that they have there, like in the middle, that's the Boolean expression that we'd have overall.
Exactly. Right. Construct an AND expression that produces a 1, the exact combination of input values to that row, and a 0 for all of the combinations. Okay. Um, the circuit corresponding to this expression, the diagram shown, observe that expression 2.4.5 is a disjunction of terms. Right. It's an OR gate that are themselves conjunctions. And which one of P or not P, or of Q and not Q, and one of R or not R all appear. Right. R, not R, Q, not Q. I don't think we had a not P in this though.
Yeah, but we don't have to. It's kind of either P or appears or not P appears.
I see.
But yeah, we had just plain P in all of them.
Such expressions are said to be called disjunctive normal form or sum of products form. Right. It would be it looks like the product of sums if an or is the producer and the and is a summer.
Yeah, I guess maybe they're considering the and to be like a multiplication, because and I saw this some time ago, like that, uh, like for like the truth table for and is
Ah,
like looking at t as one and false or true as one and false as zero. P ends
right.
q is true just when P and Q are both 1. So similarly, if you think of it as a product, 1 times 1 equals 1, but 1 times 0 is 0 times 1, and 0 times 0 are all 0. So it's kind of like
Interesting.
yeah, the truth table, when true is 1 and 0 is false, the truth table of P and Q is like multiplication.
Right.
Like the outputs or the truth value of the whole thing is like the product of the truth values of the individual parts.
And I guess the OR gate is a sum operation in the sense that like 1 plus 1 is 2, which is not 0.
Yeah. Yeah, exactly. Yeah, it doesn't quite align with like the exact values, but yeah, it's not 0.
Yeah.
Yeah, and then 1 plus 1, 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 0 is 0.
Interesting. So, in terms of where they place the dots, see a dot here, here, and here. I don't know why is the P further out, the Q a little bit more in, and the R the most inward. Is it just because the P is up top?
I guess so. Yeah, like kind of yeah, I guess that's kind of how they made space. And I guess they decided to like put just P, Q, and R all going into the first into that AND gate, and then they soldered them like to have them go into the like the other um recognizers.
Mm-hmm. And then they only used this one dot to represent the solder into this AND gate as well as into the third AND gate. I think, let me see, they have this first dot actually up here to create this line, which would then be soldered once more.
Yeah. Yeah, so they need like two solders like to split it off at the top so that it can go into the first recognizer and then also split it off to go into the second. And then before the second, they need to have another split so they can also go into the third. And I guess
Right.
they kind of arranged it so that like the dots for a given signal are parallel to each other, so that like they're kind of organized in that way.
They are. And it looks like for a parallel of 3, you only need at most 2 dots, at least in this
Yeah,
case, for each of the variables.
yeah,
Actually,
yeah, exactly.
it looks like I did follow that rule that you only need 2 dots for this circuit.
Yeah, it did.
Hmm. And then the placement of the variables is actually as high as the highest. All of the variables are like packed up at the top left of the diagram.
Yeah,
None of the variables are underneath this black box circuit, whereas it's like its brethren are above. Like they're all kind of equal in that regard.
yeah, yeah. I guess that makes sense. I guess that kind of makes it like yeah, it's kind of like a very tangled circuit. So I guess that's how they tried to make it as neat as possible.
Interesting. Now let's see. Do we usually go on for an hour or two?
I guess like the stream we often have had 2 hours. So we could go on, or we could also do like Hearthstone.
I think, let's see here. We can probably go on because the section's almost done.
Yeah, I think we can finish it.
Now let's see here. Simplifying combinational circuits. Consider the two combinational circuits shown in figure 2.4.8. Okay, we're going to simplify them. So with P and Q, I'm guessing they're equal or something here, but like
Yeah.
there's
Yeah, like they're equal in the sense that like for each combination of inputs, you're gonna get the same output for either of them.
right,
Yeah, and it would be kind of nicer to have the lower one if you can. So it's good to be able to simplify.
right. Um, See, there's the and at the end. There's an or coming up here, and it's oring an and. So there's another and right here. Between these two.
Yeah. Yeah, and I guess oh yeah, exactly. Yeah, the P and Q is going into the OR gate. Um and then also going into the OR gates, you got a P going into an AND gate and then a not Q. So yeah, P and not Q.
Okay.
Yeah, I think that's what it would be. Yeah, with the parentheses.
Since it's P and
Yeah,
Q,
that's pretty complicated.
since it's
Yeah,
P
it's
and
pretty
not
complicated.
Q, or P and Q, that would be the equivalent of just P, right?
Yeah,
So it is just like P and Q.
yeah,
Okay.
yeah. So I think what they're getting at is like the circuits are equivalent because like for any input output pair, you'll get the same output for either or sorry, for any input pair, you're going to get the same output for either circuit. And then
Yeah.
that corresponds to logical equivalence, like the Boolean expressions are going to be logically equivalent.
Yeah.
Yeah. Oh yeah, and you have that there. Yeah. Yeah.
Okay. Hmm. The logical equivalence can actually help you optimize your circuitry to save space and power.
Yeah.
That's cool.
Yeah.
I guess it also saves space and like brain power as well.
Yeah. Yeah, definitely. Yeah, and it's nice how like logic can help you see how to do it more simply.
Yeah. Two digital logic circuits are equivalent if and only if their input output tables are identical. Since logically equivalent statements forms have identical truth tables, you can determine that two circuits are equivalent by finding the Boolean expressions corresponding to the circuits, ensuring that these expressions, regardless or regarded as statement forms, are logically equivalent. Nice. I wonder what other things can be represented as Boolean expressions, which can then be simplified using logical equivalence. We know that conversational statements can be, and we know that circuits can be.
Yeah. Yeah, I wonder what else. I think the next section might have like another application.
Really?
Yeah, I'm curious about. I think it involves something to do with like um different like binary digits or something like that. Maybe it's related to circuits, but I wonder what that'll be.
Hmm. Showing that two circuits are equivalent. Find the Boolean expression for each circuit in figure 2.4.8. Wait, I think we did that.
Yeah. Oh yeah, we already did. and then show that they're logically equivalent. Well, I guess one way to show that they're logically equivalent and that the circuits are equivalent is just to use a truth table and show that, like in every row, you get the same, uh, like output truth value, or you get like the same truth value for each expression. But I guess they want us to use theorem 2.1.1, which was like different like rules of logical equivalence. I don't exactly remember all of them, but we could kind of work through what they have and like see how each step works.
Yeah, I remember this one, which was like P and not Q, or P and Q is equivalent to P. I don't remember the
Yeah,
name though.
yeah, I don't
Um,
remember the name either. Um, but yeah, that is a good logical equivalence.
let's see. Hmm, I wonder if this thing lets me make tabs. Kind of does. Fallacy.
Oh yeah, so we can look at the theorem.
Yeah, I think it was around
Yeah.
here. So, oops.
Oh, there. Is that one? I think it's that one.
It's just, so it would be in here somewhere.
Yeah, maybe it was like in an example that they showed that.
Huh. Wait, it had to be somewhere.
Yeah, maybe it can be like proven using those.
I mean, I like the fact that it kind of came to me as if I'd read it as a theorem, even though it might not have been a theorem. You think it was just like a deduction based on theorems, but like,
Yeah, maybe. Yeah, maybe it was an example where like that was shown using these.
and yet not a theorem itself.
Yeah. Well, I guess it would be a theorem, I guess, because like if it's proven based on like other theorems,
Right.
then it's a theorem itself.
Let's see. Uh, maybe. Huh.
So we don't have any like tautologies or contradictions. We do have, I guess, well, we like in the we have P and not Q or P and Q, and I guess we could technically use like the distributive law maybe, and the distributive law says like something or no, uh, or yeah, I guess yeah, like something or something and something. So this would like give us mm, P or Q and P or R. So I guess maybe we would have like P and not Q, uh, or P and not Q, or P and not Q, or no. Let's see. Um,
Maybe P and not Q, or P and Q is equivalent to something.
Yeah, yeah. Well, it is equivalent to P, but
Something intermediate
yeah, I
step.
guess yeah, I think we could use the distributive laws because like the distributive law on the right, number three, so it says P or Q and R is equivalent to P or Q and P or R. So like in this case, we have the P is P and not Q. It's like the thing on the left of the disjunction. And then we have disjunction or something or a conjunction. So we would have like P and Q or P and Q that's equivalent to P and not Q or P and P and not Q or Q, I think.
It looks like, yeah, so P and not Q or P and Q. First of all, that would be equivalent to P and Q or P and not Q, right? We can change we could replace not Q with R here.
Yeah, except though I think we have to use the distributive law on the right rather than that one because the one on the left there we have like something conjunction something, but like in our expression above we have like we have a disjunction originally.
Oh, I
So I
meant,
think we need to use like the one on the right that's like P or Q and R.
but what if we use the one on the left, but just use the right side of the logical equivalence?
Oh yeah. Oh, that's a good idea. Oh
Yeah.
yeah.
Then
Oh yeah, because they go both ways. Yeah.
yeah.
That's actually gonna work better. Yeah.
Then we end up with P and Q or not Q. And we know from this that, oh wait, no. So Q or not Q. I guess that would be this over here, right? We can use the negation
Yeah.
law.
Yeah, exactly. And that's logically equivalent to T.
So we would have P and T. And then we know from the identity law that P and T is equal to just P.
Yeah.
So
Oh yeah. And
yeah, distributive law into negation law into identity law would allow us to. Well, I mean, I guess we'd also use the commutative law to organize
yeah.
it the way we want.
Yeah, because we like in the original step, using the distributive law, we would originally get like P and not Q or Q, and then we would use the commutative law to turn that into Q or not Q.
True. So the commutative law can come first or second there.
Yeah. Or I guess it would uh it, it would come yeah, it would come second. We'd have P and not Q or Q, just applying the distributive law. And then we do the commutative law to get P and Q or not Q.
Let's see.
So reversing the positions of the Q and the not Q.
Couldn't it also come first if we replace, like, if we use this right version of the commutative law
Oh
to
yeah.
change
Oh
the,
yeah.
yeah,
Oh yeah, we could just switch the order of the P and not Q and the P and Q, yeah.
interesting. Now let's see if
Yeah.
the,
Oh yeah, so it could be either way. Yeah. Yeah, and then that's how we would do it. Yeah, because then we would have P and Q.
right, and we're correct. These exact same four.
Yeah.
Wait a second. Yeah, looks like all the work was just simplifying that part of the compound statement.
Yeah.
Interesting. Okay, follows the truth table. Um, truth tables are the same. Hence, the input-output tables for the circuits corresponding to these expressions are also the same. So the circuits are equivalent. In general, you can simplify a combinational circuit by finding the corresponding Boolean expression using the properties listed in theorem 2.1.1 to find a Boolean expression that is shorter and logically equivalent to it when both are regarded as statement forms, in constructing the circuit corresponding to the shorter Boolean expression.
Yeah.
H.M. Sheffer. So, NAND and NOR gates. Another way to simplify a circuit is to find an equivalent circuit that uses the least number of different kinds of logical gates. Two gates not previously introduced are particularly useful for this: NAND gates and NOR gates. A NAND gate is a single gate that acts like an AND gate followed by a NOT gate. A NOR gate is an OR gate followed by a NOT gate. Thus, the output signal of NAND gate is 0 when and only when both input signals are 1. And the output of an OR gate is 1 when and only when both inputs are 0. The logical symbols corresponding to these gates are, I think, the Sheffer stroke
Yeah.
for NAND and Pierce arrow for NOR, where this pipe is called the Sheffer stroke and the down arrow is called the Pierce arrow. Thus, P NAND Q is logically equivalent to not P and Q, and P NOR Q is logically equivalent to not P or Q. P NOR Q, I guess in English it would be not P nor Q. Wait, is that correct?
Yes. Yeah, like neither P nor Q.
Yes,
I
neither
guess
P
I
nor
think it would
Q.
be because like by De Morgan's laws, like not P or Q is equivalent to not P and not Q.
I just like how P nor Q seems to say that P is true, but nor implies that both are untrue.
Yeah.
I guess just with the word nor, you don't have to specify not P.
Yeah. Yeah, exactly.
Table below summarizes the actions of NAND and NOR gates. Okay, they still have the little dot to differentiate the NAND gate from an AND gate and to imply the NOT gate.
Yeah.
Okay. They called the truth table action. It's neat.
Yeah. So it's kind of like describing the action in the sense of like what happens to the input signals.
Yeah. It can be shown that any Boolean expression is equivalent to one written entirely with Sheffer stroke or entirely with Pierce arrows. Thus, any digital logical circuit is equivalent to one that uses only NAND gates or only NOR gates. I wonder if they're also saying that any digital circuit can be represented by only NAND gates or only NOR gates.
Yeah, I think they are because like or unless there are like other kinds of logic circuits, but the ones we've been looking at, yeah, I guess you could
Right.
always do it with just NAND gates or just NOR gates.
Even though they only said that it can be shown that any Boolean expression is equivalent to one written entirely. Maybe saying that any Boolean expression is equivalent to one implies that one exists.
Yeah. Yeah, exactly. Yeah, because otherwise it wouldn't be equivalent to any.
Oh, okay.
Yeah, and then because the Boolean expression is equivalent to one, with entirely Sheffer strokes or Pierce arrows, that means that the circuit is equivalent, like it has the same action as one that has entirely NOR gates or NAND gates, which I guess kind of makes sense because like the Boolean expressions use not, and or. Uh, like the not part is included in both NAND gates and NOR gates, and then
Oh,
yeah, and then each of them includes only and or, but like you can use De Morgan's laws to like uh to express like and statements in terms of or statements or vice versa.
true. Rewriting expressions using Sheffer stroke. Okay. Using theorem 2.1.1 in definition of Sheffer stroke to show that not P is equivalent to P NAND P.
Yeah.
What?
So I guess we first gotta like write what does P NAND P mean? And it would mean like not P and P.
So let's see. Okay. Well, I guess that's one step further because it would actually be P and P followed by a not gate, so it'd be not P and P.
Yeah, and so there would be like a not, like the P and P would be in parentheses, and then there'd be a not applying to it. But yeah, exactly. In terms of like the circuits, you would have like the P is going through an AND gate and then through a NOT gate.
Okay. And then
Yeah, and I guess so we got to use that theorem again to show that equivalence.
so let's see. We have not P and P. Would we use the Morgan's law to get not P or not P?
Yeah, I think so. Yeah, exactly. And then we have so not P or not P, then that's by the idempotent laws, that's equivalent to not P.
Okay. So De Morgan's law into the idempotent law.
Yeah.
And then for this one, P or Q is logically equivalent to. Oh, wait a second. Yeah, P or Q is logically equivalent to P NAND P, NAND Q, NAND Q.
Wow. Yeah, so I guess we'll first start by writing what that is by definition, that using the definition of NAND. And I guess like what P and N P is like not P and P, Q and N Q is not Q and Q. And then so we have a NAND between both of them. So we have like not P and not Q and Q. Those are joined by an and then the whole thing is negated.
Okay. So we can use the Morgan's law and the idempotent law again to end up with not not P and not Q.
Yeah. Yeah, and then we
Um,
can use De Morgan's law again.
to end up with P or Q.
Yeah, and then with one intermediate step, because first we'd have like not P or not Q, and then we
Right.
use whatever that law is called.
It's a double negative law.
Yeah, oh yeah, the double negative law. And that tells us that not P is equivalent to P and not Q is equivalent to Q. Yeah.
Nice.
Oh, cool.
Let's see. Yeah, idempotent law. They didn't mention the De Morgan's law.
Um, oh yeah.
Let's see. They said by idempotent law for and.
Oh yeah, this is another way of doing it because like P and P is equivalent to P, so you can just replace the P and P with P, and then you have not P.
Oh.
So I
Okay.
guess there are multiple ways to do it.
Yeah. Or I guess yeah, you didn't necessarily have to do the Morgan's law. Then you could have just for that particular one, you could just do straight to the idempotent law.
Yeah.
But then in this one, looks like they started with double negative. How do you start from double negative here? Oh, it applies to right there. It applies to the P or Q. So you would end up with, wait a second.
Yeah, I think they're doing it in the reverse direction, which seems kind of harder, but
I mean, where do they get this not P or Q? So I guess their representation of, like, where is the or coming from in any case?
yeah, I think they're kind of like what we did was we started with the right-hand side, P and end P and end Q and end Q, and then we figured out what that was by definition, and then we reasoned our way, like we showed that that was equivalent to P or Q. They're kind of doing the opposite. They're starting out with P or Q and showing that it's equivalent to the NAND expression. So the first part doesn't involve the definition of NAND. It's just like we start out with P or Q, and anything is equivalent to not
Oh, I
itself.
see.
Yeah. So P or Q is logically equivalent to not P or Q. And then they use De Morgan's laws, like the negation of an or statement is equivalent to the conjunction of negations. So we'll have not P and not Q.
I wonder what do you call this process? Because we did simplification, right? We started with the more complicated NAND gates and then simplified it down to the other statements. But what they're doing, and I guess the point is to take these regular statements and represent them as NANDs or NORs. But it wouldn't
Yeah.
be called simplification though.
I don't know,
Like,
it's complexification.
right.
Yeah.
Let's see.
Yeah,
But
that's
okay.
interesting. Yeah, because they're using the result, because I guess part A we've already proven, so we can use it later. So it was shown that not P is equivalent to P and AND P. So then that means that not, so we can replace the not P with P and AND P, and we can replace the not Q with Q and AND Q.
Oh,
And
you're
then,
right.
yeah, and then the next step, the definition of NAND is like the negation of a conjunction. So this is by definition P and AND P and AND Q and AND Q.
Interesting. Okay.
Yeah, that's cool. So yeah, it goes to show that there are many different ways of proving a logical equivalence.
I think, oh, we can also do these test yourselves.
Yeah.
So the input output table for a digital logic circuit is a table that shows.
Mm. I guess it like shows all the possible combinations of inputs and the corresponding outputs. And kind of like showing the action of the circuit on the inputs.
Yeah, all possible, I guess, outputs for given inputs. Or and to be specific, we can use that lingo of action, right? Like
Yeah.
is the action of a circuit by
Yeah.
showing all possible outputs for all possible inputs. Boolean expression that corresponds to a digital logic circuit is
Like a statement form that corresponds to the input output table, I guess, or yeah, not sure how to how best to describe it.
the Boolean expression, the Boolean expression that corresponds to a logical circuit.
Is like, and maybe it's like it's a it's a statement form whose truth table like has the same combinations of
Right.
or like a statement form that has the same truth. Yeah, I don't know, like how. Yeah, I don't know what a good concise way of explaining it is. Like it's like that for like the correspondence between combinations of truth values for the individual statement variables and truth values of the whole statement form is the same as the correspondence between a combination of inputs and an output. But I wonder how
Right.
they, yeah, I
It's
wonder
the,
how like what a concise way of describing it is.
I would say whose truth table, I mean, I guess it might be incorrect to say is equivalent to the digital logic circuit's input output table,
Yeah,
or I could say corresponds with.
yeah, yeah, that's a good way of putting it.
Recognizers for digital logic circuit that um outputs a 1 for only one given combination of inputs.
Yeah, yeah, exactly.
Two digital logic circuits are equivalent if and only if their input output tables are equivalent, right?
Yeah, or like they have the same input output tables.
Yes.
Yeah, which means that for any combination of inputs, they have the same output.
Yeah. I wonder if it's for any given inputs that have the same output.
Yeah. Yeah, I guess they would, because like you pick a particular combination of inputs, then you plug it into either of them, you'll get the same output.
Let's see. An AND gate is constructed by placing a blank gate immediately following a blank gate. So it's a NOT gate following an AND gate.
Yeah,
And this one is placing a NOT gate following an OR gate.
yeah,
Nice. Let's finish this chapter in 1 hour and 45 minutes.
yeah,
At
yeah,
least
yeah, that was fun.
that section. So now we can have a best of 5. No, a best of 3 out of.
Yeah, sounds good. Yeah, that was a good kind of gateway to electronics.
It really was.
Yeah. Yeah, I can play some Hearthstone. Yeah, actually got a new deck, the Lich King, so I'll try that one.
Oh yeah, I saw that. Let's see. Okay. It's a really strong card.
Yeah. That's a good move. Oh, it still has 2 health, so yeah, I guess I'll looks like you win this one.
Yeah.
Yeah, congratulations. That was a good game.
Right. That dragon move won it for me.
Yeah. Yeah, that was a great one. And I think I see you got the card that gives you 40 cards.
Yeah, exactly.
Yeah, yeah, that's a good one. Okay. Do another. Oops.
Did you pick the wrong deck?
Oh. Oh, I just didn't know if like if I click choose, will it still be like it'll stay like a oh yeah, there you are. Okay.
Hmm. Hilarious.
Yeah. Uh, four of those in just a couple turns. Yeah, that was a good game. Yeah, that Hydra card is very powerful.
It is, although I miscalculated. I thought that its heads always had a rush. But I think it's just the first heads.
Oh yeah, yeah, I guess so.
Yeah.
Yeah, yeah, I guess that was interesting with the devouring the minions. I guess if they're like, I guess whoever does it last ends up winning if each player
Yeah.
has those cards.
If each one has two. True.
Yeah, yeah, but I got lucky. Like on that last turn, I happened to draw the devouring minion card.
Ah.
Yeah, but yeah, it's a 1-to-1. So should we do one more?
Yep.
Okay. Wow. Yeah, that's a great card, yeah.
Good game. I think
Oh, great.
on that turn after you summon that colossal minion, I feel like you
Yeah.
should have just attacked me directly.
Yeah, I was debating whether to do that. Yeah, I guess yeah, I guess I could have.
I would have
Or
still been,
actually I should have because if I had attacked you, then I could have just dealt one damage with the hero power, and then I would have won.
yeah.
Oh yeah.
I
Oh
mean,
yeah.
I think
That
I would
makes
have probably been barely alive, but I don't know, having such little HP, and
Yeah. Oh yeah, definitely. Yeah, that would have been the right move there. Yeah. Yeah, congratulations. Those are fun games.
those were nice games.
Yeah.